work through this as best as I can, but we'll see how far I get. So here's a little bit of background information about me. The last bullet on there are a couple things I enjoy in the high power rocketry area. I like high altitude staged rockets. I've been doing that for probably 15 plus years, I guess. And about 7 years ago, I started messing around with vertical orientation systems. And I've had a lot of fun with them, and I decided I'd try to do the presentation today talking about sort of the journey for the last 7 years or so in this area. So by way of agenda, I'm going to talk a little bit about what vertical orientation systems are. And then I'll talk a little bit about the capabilities of the system that I've been using for that time and how it's kind of evolved. I'll talk a little bit about some of the flights and some of the benchmarks along the way, I guess, that were interesting. And then I'll talk last about future development, and I'll introduce something I'm calling the BOSS 2 system, which is a second generation stabilization system that hopefully is a little bit easier to use and a little bit more user-friendly. And then the last thing will be I'll talk about some beta testing that is just getting started. So let me start out just defining what a vertical orientation system is. It has three major components. One is an inertial measurement unit to collect data on the movement of the rocket. Then you need some calculations to take that data and convert that into what is the orientation of the rocket over time. And then if you want to control the orientation, you need a mechanical system that will correct the calculated orientation to the desired orientation. And that mechanical system can include canards or gas thrusters, moving fins or gimbal nozzles. And everything that I've done so far has been based on canards. So that's really all I'm going to talk about. There are some other words that can also be used to describe these systems. Active is a word that's used a lot. Stabilization is used a lot, although I don't really know why, because the systems don't stabilize anything. They control the orientation of the rocket. So the idea is to control the orientation of a rocket, and you can either control the tilt or the bearing, roll rate, roll angle, things like that. And what those things are doing is controlling the approximate trajectory of the rocket. And the reason I say approximate is because if you're using something like canards or fin tabs or something, they're not going to work very well at low velocity. So you're not really controlling the trajectory at that point. They also are not perfect systems. You may say fly vertical, but it may fly 3 degrees off of vertical just because of the accuracy of the equipment. In the case of a gimbal rocket, you don't control the trajectory of the rocket after the motor burns. And the final factor on there is that the trajectory is affected by external factors such as wind. So when you add up all those things together, what you're doing is controlling the approximate trajectory, and the vertical orientation systems are not really very good at guidance. So I think there's a lot of misconceptions about what these systems are. They're designed to control orientation and the approximate trajectory, but they're not guiding anything. But the primary value of them, the way I see it, is they control the dispersion of the rocket. And I've got some examples on here. So let's say you're flying at the Kern Municipal Airport, which I get to go to every now and then to fly rockets. And you can see on there there's a launch location, and we got some wind And so if you're not using any sort of a system that controls where the rocket goes, the landing location could be that entire oval. And so you can go pretty much anywhere. You might weathercock into the wind and then drift back a little bit, or you might not weathercock. And you might drift downwind a long ways. So you don't really know where you're going. But on the other hand, if you're using a vertical orientation system, you have a much better idea of where the rocket's going to land. So you can, even though you don't know exactly where the rocket's going to go at apogee, you have a much better idea than if there's no control at all. And then if you combine that with an upper level wind forecast, you get a pretty good idea where the rocket's going to land. And I've tried this probably, I don't know, maybe a dozen times, and I can typically land within a few hundred feet of where I think it's going to go, versus something that might be miles in terms of dispersion. And I also have something I call a near vertical flight, where you don't necessarily fly vertical, but maybe you fly at a small angle. I sort of pick a number of like 12 degrees. And I can fly at 12 degrees in one angle or another angle. And if I do that, I can refine the landing location even further. And so maybe you have one landing location that you like, it's better than the other, and you can sort of tailor it. And I actually tried this like a couple months ago, I guess, basically similar to what I was just showing. And it's going to be a little hard to tell here. This was the launch location, and I basically told the rocket, fly 12 degrees to the west. And so it does that. And it turns out there was a little more wind than I thought on the way up. So here's where I thought the rocket was going to be in apogee. But it's only approximate, and here's where it actually was. And as it turns out, the wind was a little bit more from the south, and I didn't believe the weather forecast. And I also almost outsmarted myself and landed in the trees when I got there. But even though that almost happened, I'm still not all that far away from where I thought I was going to land. So if you kind of compare that to an uncontrolled flight, where you have literally no idea where you're going to land, or not a very good idea, it can be a huge improvement. And so I kind of think it's something that would be good for people that fly at tight fields or places where there are hazards you want to avoid, tree areas, woods, that sort of thing. So as I said, I started working on this about 7 years ago. The original inspiration for it was Alyssa Stenberg's NARM presentation, and I don't know if you've ever seen that, but she got up and talked about using the Guardian RC autopilot to take basically a model rocket and go vertical with it. And I thought, hey, that looks like a lot of fun. And so I started using it. I started making some phone calls. And I talked to Frank Hermes, who's the gentleman that does the rocket tiltometer back a few years back. And he introduced me to a gentleman named Dr. Bill Tremelani. And I don't exactly know how to describe his capabilities. He's a really smart guy, and he's the brains of the operation. So we were originally going to use something that he developed called the Universal Development Board, and we were just going to use it for data logging because the Guardian doesn't have that capability. So we were just going to ride along with the UDB. And we looked at it a little bit, and we discovered, what the UDB can do everything, and the Guardian can do, and plus you can program it. So we just abandoned the Guardian, and I never actually flew it in flight, even though I looked at it for a while. And so we've been kind of working on this thing for about 7 years now, just on and off. And every now and then we'll go through a spurted development and add some new capabilities, and then do some flights and look at the data and come back and add add some more stuff. So as I mentioned, the control system is designed and programmed by Bill Permolani. I'm just the guy that flies the rockets and builds the hardware. And I get to have more fun, I guess. It was co-developed with Spark Fund, and there's some information on the CPU and the gyros that are used. The flight program is a heavily modified matrix firmware, and that was originally done for drones and RC aircraft, and we've made just literally dozens and dozens of changes to that program to make it suitable for rockets. And I mentioned you have to have a calculational scheme for keeping track of the IMU data, and in this case, the technique is called direction cosine matrix, and I'm going to tell you absolutely nothing about that at all. The board is set up to have a sequential pulse width modulated outputs, so it makes the battery management a little easier. There's a bunch of other capabilities that we've added to it over time to try to, you have to take the signals from the flight program and convert those into canard movements and optimize all the ranges and stay within the capabilities of the gyros and the other things that are on there. And so we've done a lot of that. We also have a launch detect algorithm in there, which is important because when you're using a system like this, you have to, once you launch the rocket, you lose gravity. So you have to tell the system, don't look at the accelerometers anymore for determining which way is down or for doing anything with the gyros. So equipment that does tilt measurements, like the altispectrum equipment, for example, it does the same thing. It basically ignores the accelerometers once the rocket is launched. In the systems that I've done, I think a lot of people talk about using sophisticated PID control. I actually don't do that. We've had lots of success using just basically proportional control for yaw pitch. And we've added something called heading hold, which is used for helicopters, is where you mainly run into that. And that's actually a form of integral control. So the system has kind of evolved where we can control the tilt and bearing of the rocket through the flight. And you can basically, we have a spreadsheet that you can program up to 100 changes in tilt and bearing through the flight, so you can fly patterns. So far, I've only done 45 changes in bearing, and I'll show that flight in a bit. But it's pretty interesting to try to figure out, well, how fast is this rocket going to turn, and how fast can I make these changes in bearing and tilt, and actually have it go where I want it to go. Another thing that's pretty cool is that the gyro offsets are determined on the pad just before the flight. In many cases, you might measure gyro offsets and just sort of hard code them into your flight program. But the system that we have actually measures those things while the rocket's on the pad. And the rate of that adjustment is set up so that it's slow relative to the things like wind movement and so forth. But it's fast relative to launching the rocket without having to wait too long. So it's sort of optimized in that respect. And this just shows some actual data prior to launch, where the gyro offsets are being measured as the rocket's sitting on the pad. And you can see it takes about 10 minutes to basically get everything lined out before you launch, but you're seldom going to launch faster than that anyway. So that's a good time frame. The mechanical design of it, I just use digital RC servos. I don't have anything exotic in the system that I use. But digital servos are nice because you can set the center point and the end point on the ranges, and it's a way of controlling game. It's pretty convenient. I use direct drive canards. I don't have a system in there for gearing down the canards, and the reason for that is I want the fastest response that I can. One of the things I learned early on is that when you're flying a rocket that has canards on it, there's not a tremendous amount of torque on the canard if you balance the canard, but there is a lot of lateral force from drag, and so you really have to support the servo spines, or you'll just break the servos. And I'll kind of show how I do that. The canards that I use, I just use flat canards that are beveled, and the reason I do that is so that I can very accurately align the canards with the airframe. If the alignment is not really good, then you're going to have turn or roll that you don't really want in the system. So it's more important to be able to line it up well rather than to maybe have the best airflow on the canards. I just have a few pictures in here about how I've used the system. I started out original testing, and you can kind of see the canards up at the top of the rocket there. And that was some of the original testing that I did, and I've done it sort of that way, and I've also done two-stage rockets with the canards up on top of the rocket as well. But where I really built the system was to be used for two-stage rockets. And if you look closely at it, you can see the canards are right here. And the idea is you launch the rocket on the booster, and then the booster drops off, and then you steer the rocket back to vertical from below. And so during the coast period, you're bringing the rocket back to vertical, and then just before the sustainer motor lights, the stabilization section falls off and recovers under its own parachute. And that's the real reason that I built it. And I've done it on two-stage rockets, and I've also done it on three-stage rockets where I brought it back to vertical.
Is it the two different canards, one on the lower and one on the sustainer?
No, just one set.
Okay.
Yeah, just one set here. But it's a three-stage.
Oh, I see.
And one of the things that I found, and I'll talk a little bit more about it in a bit, but when you have canards ahead of fixed fins, you can get an effect called control reversal, where the vortices from the canards will interfere with or interact with the fins and actually turn the rocket in the wrong direction. So I don't know if this is going to work, but I came up with this spin cam that I can put down underneath the canards for the purpose of avoiding as much as possible that control reversal phenomenon. So for this presentation, I put together sort of a table of the flights that I've done with this system, and it surprised me that I've flown it 30 times. I thought it was more like around 20, but it actually turns out to be about 30. And to be perfectly honest with you, I can't wait to fly the next one, because this is so much fun. It's just a lot of fun to do it. So I have a few milestones on here. I'll just explain the chart. I got the years off to the left, and months are on the top. And green is a good flight, yellow is and red something bad happened. So the first good flight was really the third flight, and this was where we actually saw pretty convincingly that the flight was vertical. We flew to about 4,000 feet, and we didn't have any roll. And I got some videos I can show you. You can see here basically there's no roll on here. It actually went pretty vertical. So I think that was the first time we convinced ourselves that yep, we're doing something good. Now, as it turns out, there was a whole lot of bugs in that program, many of which we found later on. But at least over that particular flight envelope, we were successful in showing that the system would work. And then, as I say, one of the things I really wanted to do with the system was to be able to use it in this two-stage mode where the booster would drop off and you could steer it from below. And so the first demonstration of that one was on that point. And you can see the booster falls off there. And then it's going to stabilize for a while, and a little bit later on, the stabilization module will fall. Get that one in and recover on its own. I mentioned that it's really important to control the forces on the servo spines because they're not really intended to handle that kind of a force. So we looked at it and we came up with a system where we can literally mount this bearing and it just happens to fit the wheel of the servo and put that in the airframe. And once we did that, we stopped having problems with mechanically with servos and so forth. And it's a very critical part of it. And I think that's when I see people do these systems, one of the things that they often leave out is something that controls the forces on the servo, and they just end up not working. Yes, sir.
Are most of these flights, before you jettison the controls with the canards, are they subsonic?
Most of the flights I've done are subsonic. And some of the 2 and the 3-stage flights, they're supersonic.
Right, but are you going Mach before you jettison the canards?
Yes.
Okay.
Yeah, when I've used this in the 2-stage configuration, I did a large PO motor, and that got up to about Mach 1.7 or something, and was doing the stabilization at that speed.
And are there any issues going Mach that you discovered that you didn't have?
Servo spines. That's where we kind of learned the lesson on the importance of having that supported. So I mentioned the control reversal, and this is a picture that you cannot see, but you can get these vortices off the canards, and they'll go back and they'll hit the fins, and under certain conditions they'll actually turn the rocket the wrong way. And I had a really good demonstration flight of this a few years back, where if you look at this closely, you can see that the canards are trying to turn the rocket in the opposite direction that it's turning, because the canards are interfering with the booster. But as soon as the booster falls off, the control reversal is gone, and roll is controlled. So it really was a very convincing demonstration that occurred. And having gone back and looked at some prior flights to that particular one, I also noticed there were some other flights where I could at least make a case that the same thing happened. So it was from that that I went ahead and designed the spin cam. And I've certainly seen cases since that time where I'm pretty sure if I didn't have a spin cam on this flight, bad things would have happened. So one of the things that we wanted to do was basically just demonstrate that we could make a rocket go vertical. And so we did a number of flights where, there were variations on the theme, but a number of them were to have the pad tilted and then show that it could go vertical. And then we did some where we launched it vertical and we made it turn, and then we went back to vertical. And, things like that, just to kind of demonstrate the different capabilities that we have. And this is one flight that I particularly like, and I wish I had a good movie of it. But it actually weathercocked to probably about a 30-degree angle, and then just kind of slowly over time, just gracefully went vertical. And if you saw it live, it was a really cool effect. And you can just watch the smoke ring on the left frame there, and see how that went, how it kind of went vertical. It was a really interesting flight. And then also during that time was a flight that I did to a 3-stage flight where I flew to 175,000 feet, and I used the system on that flight. And if you look at the data, the time and tilt, this initially was the period where the system was not controlling. So the booster burned out here, the booster falls off, and then there was about a 6 or 7 second period where we were trying to bring the rocket back to vertical. And you can see that if we didn't have that coast period might have gotten up as much as 10 degrees even. But the system managed to bring the tilt down to about a degree and a half or so at the time when the sustainer landed. So that rocket went to 175,000 feet and landed less than 3 feet, or 3 miles from the pad. Then we started doing some flights where we were trying to control not to vertical, but to near vertical, as I call it. So basically demonstrating that we could turn and fly at a specific bearing, and that's not far from vertical, but maybe far enough to where you could use it for something useful. And so this is a flight where we launched the rocket about 5 degrees to the left, and then told it to fly 10 degrees to the right. And it did that. So I think we started feeling pretty comfortable that we could control the bearing as well as we could control the tilt, I should say, and the direction in which that tilt occurred. And then we decided, well, if we can control change the bearing of the tilt, once or twice in a flight, we can do it dozens of times in a flight. And so we set up what I think is one of the better flights that I've ever done, which I call the infinity flight. How many of you have seen that video? Come on. All right. Okay, so the idea was to launch this as a 2-stage rocket, and it's like a K-2050 in the booster. It just gets it moving. And then I had a long burn, L395 in the sustainer. I think it's like a 15-second burn. And during that 15-second period, we flew the rocket at a constant tilt of 7.5 degrees, and then made 45 changes in the bearing. And so we just basically flew infinity signs up to half. So here it's going to make the 7.5 degree turn, and now it's going to start flying infinity signs. So I thought that was a pretty good flight. I was thinking about trying something like that here, but it just didn't work out. So the last flight that I want to talk about here is the demonstration of the second generation of the stabilization system, which I call on the BOSS-2 system. And so I did a demonstration flight of this a couple months ago now, I guess. And this is the flight I talked about at Hearn a little bit ago, where I launched the rocket to the west, and I told it to fly at a 12-degree angle to the west. And you can kind of see from the GPS that it basically did that. And you know, the nice thing about it is you can fly at that tilt, but the system will continue to try to hold that angle all the way to apogee. So instead of going up and weathercocking and having a high-speed deployment, basically it continues to try to hold that angle, and you have a soft deployment. So you can fly at an angle, but without generating the high speed, high horizontal speed. And so I think that's the main thing to look at here is flying at that 12-degree angle right now. But if we look at it as it gets to apogee, it doesn't have a lot of horizontal velocity. So I just wanted to kind of tick through some of the lessons learned in the process of testing and developing the system. It's really important if you're doing more than just a model rocket flight to basically turn off the accelerometer so that they're not used in the calculation. And it kind of limits the applicability of the off-the-shelf RC autopilots that people talk about using for this purpose, because they'll work for a certain amount of time, and then you just lose vertical. Another thing that's important is you have to stay within the gyro limits. If you get outside the gyro limits, basically the system gets lost. And so we've kind of found over time the 1,000 degree per second gyro setting range seems to be about optimum, because you seldom go with a turn rate that's faster than that. But if you set it at 2,000 degrees per second, for example, you start losing some resolution. So that sort of is the optimum. And I see a lot of people comment on these systems about, oh, don't use that system during boost. You know, you just wait until the motors burn out and then turn it on. And I don't know where that comes from. I don't have any issues that I've seen. The system doesn't know it's under boost or not under boost, and there's no reason not to try to control early on. So when I hear people say that, there's really no technical reason that I know of to do that. I talked a little bit about the servos having to be protected from the lateral forces. Another lesson learned is you got to have data, and if you don't have the flight data, you don't really know what happened in the flight. And it's one of the things that makes doing this fun, because after you do your flight, when you got all this data on the accelerometers and gyros, and everything that goes along with it, and so you can study that and try to figure out why it did what it did. And one of the things that I've used that data for is to try to understand how fast can I turn a rocket, because I can calculate how fast I can make a rocket spin, because I know what the moment of inertia is. It's fairly easy to do that force calculation. When you're talking about yaw pitch, things like the stability of the rocket come into play, and it's much more difficult to figure out how fast it's actually going to turn. And indeed, when I started doing this, I had flights where it went to vertical, maybe took 5 seconds. I said, well, is that right? Does it really take that long? And it turns out that's how long it takes, if you're doing it. So I took a bunch of flights, and they've got noise in them from whatever, just tried to figure out how fast do they turn. And that kind of lets you put together some of these flights where you're varying the orientation during the flight. As I mentioned earlier, I think relatively simple controls work. We use mainly proportional for yaw pitch. We do have some derivative thrown in there in case the rocket gets moving too fast back towards the control point. We slow it down a little bit. Roll control is proportional on the roll rate, but we also have the heading hold in there also, which basically keeps the rocket facing the same direction all the time. I didn't really point that out on some of the flights, but if you look at it, there's no net roll. It basically is facing kind of the same direction all the time. I see some people put together systems where the canards are going like this, and it isn't really necessary. Pretty much the maximum I recommend is maybe about a 7.5 degree turn is really about all you need in a high power rocket, and you can move the rocket pretty fast. I also found that airframe flexing is a big deal. If you're flying the system pretty hard, you can see the oscillations in the airframe as the canards release and re-engage. I actually got to the point where I put a carbon sock over the airframe on the rocket that I do most of this things. It slowed down the airframe flexing, but it's also the last sock that I'll ever use. Another lesson we learned: control reversal is real, and I'm hoping that we learn more about that in the coming months. Just how often do we really encounter it? I also learned upper level wind forecasts are not always all that great. Sometimes they miss a layer or a direction or something, and so you don't quite land where you think you're going to. You can be fairly close, but not necessarily exactly where you think you're going to get. Another thing I found is that and I'm not exactly sure how to interpret this, but I have a lot of flights where I'm over 1 caliber stable, and it looks like the rocket is initially unstable, and then once so it'll kind of develop some tilt off the pad, and then as it builds up velocity, it'll come back and orient back to vertical as it goes. But it just seems to me like the programs are over predicting the stability when you have the canards, and I don't know why, because they shouldn't be doing much at that point in flight anyway. So maybe it's the spin cam, I don't know. But I have a lot of flights like this one where it just looks like the rocket goes unstable early on, right there, and then goes back to vertical. But that's the only thing I can come to the conclusion is that this calculation from Roxin or whatever is under predicting or is over predicting the stability. So I want to talk a little bit about future development. My goal is to try to make vertical orientation systems more accessible to people. And the reasons that I feel that way is I think it contributes to safety by reducing the dispersion of rockets. We don't want to have rockets going outside the waiver. We don't want to have rockets landing in trees and so forth where we don't want them to go. Another reason is it's just very technically challenging. If you kind of think about it, there's, you've got a computer that's got to control the flight. You've got a flight program. You've got an interface with the mechanical system. You've got to understand the flight dynamics. There's a lot of stuff that goes in it. I always thought that it would be a great thing for the college students to do. So I try to encourage them to do projects like this, just because it involves so much technical areas that they should be interested And like I say, it's also just a lot of fun. I enjoy flying the thing, it's pretty much other than two-stage rockets, it's the only thing that I fly, and that I enjoy a lot. So back in 2015, my first effort at expanding this was to start a beta group, and I got 6 flyers, and what they got at that point in time was a control board and some instructions to say, hey, here's some servos you can use, here's how you wire it up, here's some hints and tricks you could use, and some of those flyers went ahead and did systems, but it just wasn't very successful. And I think the reason is, number one, it's just difficult. And not everyone has all those skill sets to be able to do it. I don't have all those skill sets. I got a guy who is my guru who can help me on the flight program. Otherwise, I couldn't do this either. So it's just very difficult for people to do, and we didn't have a whole lot of success. So it really didn't do anything for improving access to the technology. So back around December, I guess I got interested in trying this again. And so we've now started a second beta test group, and we have 6 flyers. And this time, based on what I learned the first time on this, basically what the beta testers are getting this time is a much more complete system. So that they don't have to worry about every little detail. It's pretty much ready to fly. And so they still got to design the rocket, and they still got to do everything to make it fly properly and interpret the data and so forth. But we tried to make it fairly user-friendly. And so I haven't doxed the beta testers yet, but I got one of them over here, Paul Snow's one of them. And I was hoping he was going to be able to fly here at LDRS.
I got sick for a week, so that was the problem.
Life got in the way. So 6 pretty experienced flyers, and they're going to be using the 2nd generation VOS 2 system. And so I'm also, well, everything worked except that. Okay. So as I say, it's a more user-friendly system relative to the 1st generation. It's a lot easier to charge the batteries and calibrate the canards and do some of the mechanical stuff that you have to do. And fortunately, one of the beta testers is pretty good at 3D design. So we basically are 3D printing the chassis for this, which literally reduces the time to make these systems from months to hours. So it still is not a real simple thing to do, but it's a lot more accessible as a result of that than it would have been without 3D printing. And I'm also trying to do better documentation, and I'm sure Paul would say that we're getting some user support out of it.
I found the documentation to be very good.
Good.
Better than some kit instructions, for sure.
And I'm at this point, I'm reasonably sure that a spin can is needed if you're putting the canards up there. It may be that you can control the vertical with relatively minimal canard movements and not encounter the control reversal. But for better or worse, we're going to start out with getting a spin can. And so what the user does on the spin can is takes the thing apart. Have you done that yet?
I got the fins cut out and was ready to bevel when I came downstairs.
Okay. So you have yet to discover that the ball bearings are like paper.
Well, I got the extra 50 in a little bag, and that's the scariest part to me is
People are confused and there's not enough documentation. So we'll do some gap filling. Hopefully review the documentation, improve the manuals, and do what beta testing is, which is to evaluate the performance of something in a real world environment. So I'm making these systems, and I'm kind of concerned about some of the, what these guys are going to do with it. So I went ahead and I formed an LLC just to try to avoid losing the house if someone does something silly. But that'll lay the groundwork, I hope, for expanded application of the technology. And I've produced the 6 systems for the beta test group, and I'm more than happy to make more. They're not ridiculous, they're not inexpensive, but they're still accessible. They're like, if you get the control system and the fin cam, it might be a couple K. So it's expensive, but you get a lot for it. You get a lot of understanding and experience and support in it. So I think I've acquired a Paul's project, so I'm not sure how fast all this is going to happen. So I say supplies are limited, and they really are. But if anyone is interested in joining the beta test group and flying a vertical orientation system, you can come talk to me and we'll see what we can do. So I will take any questions that are remaining.
What size are they?
Oh, that's a good question. Right now they're 4-inch. It would be relatively easy to make different sizes. I mean, it's literally quite easy.
Could it be smaller or only bigger?
Well, 3 inches is kind of hard, just because you're literally. One of the things I've done, and I don't know if you look at this, we now have the bearing on board the system instead of in the airframe. That's one of the things that made it very difficult to make it portable for other people, was you had to put those bearings in the airframe, and that's really hard. So we've put them on the carriage, but it reduces the amount of room for servos. So, I think 3 inch should be possible, but it's going to be determined.
And what do they weigh?
That part of the system with a 1 foot section of airframe is about 2.5 pounds, maybe a little bit more than that. The spin can is a little heavy because the central spine of it is a coupler tube, and you can put that on the bottom of an existing rocket, or you can build a rocket around it. But because it's got that longer coupler tube, it's a little bit heavier than maybe your fin can will otherwise be. I roll the carbon airframe for the outer diameter, leave the peel fly finish on there. So basically take that off and mount your fins on that carbon tube. And it's like a 7-gram tube, it's pretty sturdy.
Are you or any of your beta testers going to be flying tomorrow or Saturday?
No, Paul weaned out on me. No, there was one fellow who was considering flying a couple of weeks ago, but the weather didn't support it. I was going to fly a couple of weeks ago, weather didn't support it. So we're getting off to a slow start, but hopefully it won't take long before we get a bunch of beta test reports.
I may have missed this, but I was wondering, does the rocket fly reach a higher altitude when you're going vertical? Or does it, you have more drag when you're trying to right it? So I was wondering whether you get higher altitude by correcting for vertical or just letting it go.
Well, I mean, I suspected most of the time you're going to get less altitude. One reason is you just have the extra weight. And you do have the weight on the canards. Now, if you're flying vertical, the canard drag won't be very much. If you're flying at that 12-degree angle, that near vertical mode that I talked about, the rocket is actually flying at an angle of attack when you're doing that. So you have more drag. So in that particular flight that I showed, if you look at a simulation, you get about 6,500 feet on it. And I actually got about 5,500. So it'll reduce the altitude because it's literally flying at an angle of attack. Yeah.
I have two questions. One, do you think full gas thrusters would have the same problem with reversal?
I don't think so.
And then, has anyone tried doing a full spring to center to actually twist the main fins of your rears up?
I'm not sure I understand the question.
If you put the main fins on bearings and spring load them to center very tight, and then use two cables to a servo up high above the motor, you could pull on one cable and pull it at half a degree or less one way and the other way. You want to try that?
Well, I'm sure someone has. I haven't. The main reason I haven't is most of the applications I'm looking at are minimum diameter. And it's just no way to get something in there for a minimum diameter where you could do that. I have thought about it though, and what the linkages would look like and that sort of thing. But I have not encountered it.
Yeah, it would just be a bearing down at the fin. The fin would be plugged into a bearing, and then two wires coming up the tube. Perfect.
I mean,
Yeah.
who knows what these beta test labs are going to do? You never know. I mean, anybody else? Okay.
Yeah,
Time for today.